Let's solve LeetCode problem 98, validate binary search tree. Given the root of a binary tree, determine if it is a valid binary search tree. Here's an example. You've got 2 at the root, 1 on the left-hand side, 3 as the right child. This is a binary search tree, as you can see, because all keys on the left-hand side are smaller than 2, all keys on the right-hand side are bigger than 2. Let's look at this example. 5 is at the root, 1 is less than 5, and it's on the left child. So this part of the tree is a binary search tree. But when we go to the right-hand side, we see 4, which is less than 5. So remember, in a binary search tree, all keys on the right subtree has to be bigger than what's stored in the root. So this is not a binary search tree. The idea to solve this problem is the following. We maintain a range of values that all keys in the tree has to fall into. Initially, all keys have to fall in between minus infinity and plus infinity. So we check the root. 2, is it in between in this range? Yes. When we recurse on the left-hand side, we update the right bound because now all keys have to be less than 2. That means 2 minus 1 is 1. That's my right bound now. That means all keys on the right subtree has to be between minus infinity and 1. And sure enough, 1 is in between minus infinity and 1, including 1. So this is a binary search tree. The left subtree is a binary search tree. Now let's recurse on the right-hand side. When we recurse on the right child, we now update the left bound because now all keys have to be bigger than 2, right? All keys on the right subtree has to be bigger than 2. So that means they have to be in the range 3 to infinity. And sure enough, the right child is in between this range. So that's a binary search tree, and we are done. Let's look at the second example. Initially, all keys have to be between in the range minus infinity to infinity. When we recurse on the left-hand side, we update the right bound. Now this is minus 1, right? So all keys on the left subtree has to be between minus infinity and minus 1. As you can see, 1 is not in this range, and that means we are going to return false. Assume that this was minus 1, so let's change the example. So this still satisfies the binary search tree property. Then we recurse on the right subtree, and the range of the values on the right subtree has to be now between 0 plus 1, 1 and infinity. And 2 is still in the range, so 2 is in the range of 1 to infinity. So this is also satisfying the binary search tree property. Now we recurse on the left subtree of 2. This time we update the right bound by changing this to 2 minus 1, 1. So that means all keys in this subtree have to be in between 1 and 1, and this is 4. So that's not falling in this range. That means you're going to return false for this for this binary tree. It's not a binary search tree. Here is the Java code. This is the initial call is valid BSD. It takes a root. We have a helper function solve that takes root. This is the left bound, which is minus infinity, representing minus infinity to start with, and this is our right bound of the range, representing plus infinity to start with. So when we go into the helper function, if root is equal to null, we return true because an empty tree is a binary search tree. Otherwise, we check if the key that's stored at this particular node root is in between the range. If it is not, meaning that if the root value is less than the left bound of our range, or the value stored at the root is greater than the right bound of our range, then we return false. So if the key does not fall into the range, we return false. Otherwise, we recursively check if the left subtree is a binary search tree, but this time we are updating the right bound because when we go left, the right bound, all keys on the left side, left subtree has to be smaller than or equal to root dot value minus 1. Note that I am using long as for the bounds left and right. I'm using long, and the reason for that is if you look at the problem definition, they're saying that the key values can be minus integer minimum and plus integer minimum. That's why I have to use long as the bounds. And after that, if this is a binary search tree, if the left subtree is a binary search tree, then I also have to check if the right subtree is a binary search tree. But this time I'm updating the left bound, right? The left side of my bound, because I now need to say root.value plus 1. So all keys on the right subtree has to be bigger than what's stored in the root, and it has to be root value plus 1 and right. So they have to be in this range. Let's just run this thing so that you see that it actually works. Yes, as you can see, it works, and it is the most efficient code that you could write. Any questions you might have, please leave them in the comments section.